Okay, so if you didn't get to a solution, go ahead and pause, write that out, get to a solution here. Okay. Now, so this is what I got here. Mass flow rate converted to pound mass per second. We found H1 and H2. It's 4 megawatts or 4,000 kilowatts. There's a conversion factor for BTUs to kilojoules. So BTUs per second, kilowatt is a kilojoule per second. So for every kilojoule, there's 0.94782 BTUs. So there's going to be the same number of BTUs per second for every kilojoule per second. So that serves as my conversion for BTUs per second to kilowatts. There's some others in there, but that will get you there, right? And then I just ran that through my calculator, and this is what I got. So again, how did I get this? Well, I've got to be able to write a first law equation. Write a first law equation, simplify it for what I'm looking for, find my properties, and solve. Okay. If we were in class, right? So if I'm grading this as a test problem, I think this is a little too simple for a test problem. But if it were a test problem, this is a 25-point test problem. Okay, and we're in class, not online. This is how I would grade it. This is probably going to be 15 points. Well, probably 10 points for this being correct. Simplifying it correctly would get you to 15. So if you got here and this is correct, this is 15 points out of 25. That's a D. That's 60%. This shows me you know how to find what you're looking for, apply the appropriate learning objective, first law in this case, simplify it to the situation you're looking for. I would put 5 points on your properties. Okay, so you're at 20 points before you even break out your calculator. And I try really hard to build a grading scale that works that way. Now, for the online test, because you got the timed questions, what I try to do with the timed questions, I say, all right, well, given this, and I give you a whole bunch of first laws to pick from, which first law is the correct one, for example, right? And so out of the 15 points, 5 or 6 of those would be on that timed question. Very quickly pick from a lineup which of the first laws is correct. Okay, and the rest of the points is, I try to allocate the rest of the points accordingly. Okay, if you have questions, let me know. Happy to help. But that's the first example problem. Okay, now let's look at another example here. Okay, so if you're following along in the PowerPoint. There we go. Okay. So if you're following along the PowerPoints, this is the next one. So I've got nitrogen gas flowing steadily through an adiabatic diffuser. And they want to know what is the exit velocity and what is the ratio of the area of the inlet to the area of the outlet. And they've given us some properties. They've told us the inlet pressure is 60 kilopascals. The exit pressure is 85 kilopascals. They've given me the inlet temperature, exit temperature, and an inlet speed. And so they want to know the exit velocity, the exit speed, and the ratio of areas. All right. So let's start a new sheet then. L11. This will be page 6. Another example. Okay, again, givens here. What do I know? They told me it's nitrogen gas. It's a diatomic gas, N2 gas. They've given me an inlet pressure. They've given me an exit pressure. They've given me an inlet temperature, 7 degrees Celsius. They've given me an exit temperature, 22 degrees Celsius. They've given me an inlet speed of 200 meters per second. And they want me to find the exit speed and the ratio of areas, A1 to A2. Okay. Well, is there anything else given that I've not written down here? Pause it if you need to look at it. There is something that I have not written down here that is given. Go ahead and pause. Okay, you got an answer? What do you think? Always look at the adjectives. What does this adjective, adiabatic, mean? They'll tell you it's either well insulated or it's adiabatic or negligible heat transfer. They're all saying the same thing. They've given you that there's no heat transfer. This is a well insulated device. Okay? So, alright. What are some tools I might have to find the speed and or the areas? Well, it shows up, both the speed and the areas show up in conservation of mass. So let's draw that out. Let's see what we get. Conservation of mass says, because it's a steady flow device, and yeah, they did give me that it's steady. So all the DDTs go to 0. Okay, it's flowing steady. So the n minus out equals change. The change is 0 for both conservation of mass and conservation of energy. So the mass of the inlet is equal to the mass flow rate of the inlet is equal to the mass flow rate of the outlet. Meaning, and I'm going to use, because it's a gas, I'm going to use specific volumes. So A1, big V1 over little v1 is equal to A2, big V2 over little v2. This is what conservation of mass tells me. Now, they want to know the speed at the exit. I know the speed at the inlet. I don't know the area at the inlet. In fact, they're asking me a question about the area. So I'm not going to be able to use this expression because I don't know either area. I'm not going to be able to use it to find V2. So I'm going to need another tool to find V2. But I might be able to come back here and use this to find the ratio of areas. So I think it's going to be helpful later. Okay? So let's look at first law. Let's look at the first law. Well, step 1 for writing a first law equation, you draw your system. It's a diffuser. And what crosses the boundary? Well, it's a control volume, so I'm going to have a mass at the inlet and outlet. If it's a diffuser, I know I'm going to have just mass at the inlet, mass at the outlet. It's going to slow down. It's going to change the speed of it. Okay? All right. What else? Anything else crossing the boundary? Is there any heat? Nope. It's adiabatic. It means there's no heat. Okay, is there anything doing work here? Is there anything applying a force? Is there any electricity? No, I don't see any work being done or any power input or output. So what I've got here is that if I add the ends, it's the energy of the mass in, subtract the outs, it's the energy of the mass out. Because it's flowing steady, the change is 0. The dE dt is 0. And it's one inlet, one outlet, so this simplifies down to m times h1 minus h2 plus v1 squared minus v2 squared over 2. And that's equal to 0. Now, why am I considering these kinetic energies? Steve, you didn't worry about the kinetic energy previously. Right, yeah, remember our list of 3 questions. Question number 1, is this a nozzle or diffuser? Oh, yeah, this is a diffuser. So I have to worry about the speeds. Okay. Also, they've given me the speeds, or they've given me a speed, and they're asking for the other one. So yeah. Okay. So I've got one speed here. I'm looking for this one. So I need to make sure this is the only unknown in this equation so I can solve it. Okay. What about my h's? How do we find h's? Well, first question when you're trying to find a property is, and a lot of people will say, well, you could use property tables. Yes, but be careful. That's one place, well, anyway, the first question should be, well, what is your substance? Can you find H's? The first question really needs to be, what is your substance? If it's water R134, yes, you have property tables, and we get really used to that. This is not water, and this is not R134. This is something different. What is our substance? Nitrogen. It's a nitrogen gas. It's an ideal gas. We're going to treat nitrogen, we're going to treat oxygen, carbon dioxide, and air, all of these that normally appear gaseous for us in normal conditions. We're going to consider those ideal gases. So how do I find H values for an ideal gas? Well, I do have property tables. Right? I would find them the same way I'd find U values. We talked about that in Chapter 4. How do we find U values? Well, I do have property tables. All I need to know is the temperatures. So I could use property table temperatures, and I could go look up H's, and there's nothing wrong with that. There is another way. There's something else we can do. We can also say that C sub P times delta T is approximately, and this is C sub P at the average temperature, is approximately the change in enthalpy. So I can use this because I've got both temperatures. If I can go look up a C sub P average, I can use this to quantify the change in enthalpy. So if I can quantify the change in enthalpy, I know that the inlet speed, this is what I'm looking for. This is my one unknown that I don't really know, right? I don't know m dot. We've already set up here I could find m dot through this, but I don't know the area, so that doesn't help. There's a neat trick here. If m or m dot is not given, can you work per unit mass? Can you work the problem per unit mass? Now in this case, notice what happens when I divide by m dot. We've got h1 minus h2 plus v1 squared minus v2 squared, both over 2, is equal to 0 divided by m dot. Now what is 0 divided by m dot? Well, assuming m dot is non-zero, and I think that's a fair assumption, 0 divided by anything is still 0. So I don't know m dot, but what I can do is I can work the entire problem per unit mass. It doesn't matter what the mass flow rate is. I can just basically say, well, it's a tiny little diffuser, it's an enormous diffuser. It doesn't matter. For what I'm given and what I'm looking for, in this case, it doesn't matter. Okay? So this is my simplified first law expression. If this was a test problem, you know, this would be a big chunk of the points, somewhere between 10 and 15 out of 25. This one, because it's asking for two different things, this is probably 10 points, and figuring out how to find the area would be another 5. Okay, so out of 25, that's a big chunk of points, being able to write this equation. How do you get here? Draw your system, figure out what comes in, goes out, set it equal to the change, solve for what you're looking for. In this case, I'm solving for V2. So let's do that. Let's solve this expression here for V2. V2 is going to equal square root of some stuff. So stuff is going to be 2 times quantity h1 minus h2 plus v1 squared over 2. I've got a fan going. It's blowing my paper. Right? So I think if I solve this equation here for V2, I'm pretty comfortable that that's okay. And again, I'm going to say that this is approximately equal to square root of 2 times quantity C sub P average, T1 minus T2, plus V1 squared over 2. Okay. So let's go get some properties, shall we? I'm going to need to do it this way. All I need is C sub P average. How do I find C sub P average? Well, I need to know T average. So given T1 and T2, that's going to give me T average. All right. So we said T1 is 7 degrees, 7 plus 22 divided by 2, 18. So my average temperature is 18 degrees C, and I don't know, I can't remember if the table's in Kelvin or not. So it's 18 C or 291 kelvins. I mean, my average temperature. That and the fact that it's nitrogen gas would be enough to find C sub P average. I'm almost out of time on this video, so go ahead and go find a C sub P at this temperature for nitrogen gas, and we'll start there.